Hello, everybody. Welcome to part 2 of the video for section 5.3. Last video, we talked about this example, really extended back from a example we did in section 5.2, showing you how we can diagonalize a matrix, diagonalization of a matrix, I should say. So what we'd like to do is to come up with some essentially criteria to how we can decide if a matrix is even diagonalizable. Well, not every time you have a way to kind of be able to look at the matrix and tell is it diagonalizable or not without doing a decent amount of work, but sometimes we might get lucky. Well, one of the really important condition is that if we have enough linearly independent eigenvectors, then we can say that matrix is diagonalizable. But we also know that eigenvectors corresponding to distinct eigenvalues are linearly independent. So basically, if we have then n distinct eigenvalues, then we are automatically guaranteed diagonalization. So here's a question. Is this matrix B diagonalizable? Well, we know from an example in 5.1, this is diagonalizable because the main diagonal entries of a triangular matrix, in this case 6, 8, 0, 7, are the eigenvalues of this matrix B. So the answer here is yes, it is, because we have 4 distinct eigenvalues. Four distinct namely lambda equals to 6, 8, 0, and 7. Okay, so theorem 5.6 guarantees that our 4x4 matrix B is diagonalizable because we have 4 distinct eigenvalues. This is a surprisingly meaningful example because on top of showing that this is diagonalizable, even though a 4x4 matrix can be tedious to work with in terms of EROs, right? If we want to find these eigenvalues, eigenspaces, even individually, then this takes a little bit of work. But our theorem 5.6 gives us that almost for free. But it's also meaningful for this example because we recall, because B have 0 as one of its eigenvalues, we also know that B is not invertible. That's part of the invertible matrix theorem that we add on to in 5.2. So this means diagonalizable does not imply invertibility, which, if you think about it, even if diagonal matrix, even if B is related similar to a diagonal matrix D, in other words, B equals to PD P inverse, P and P inverse, of course, are invertible. It does not mean D is invertible. So just because B is similar to D, it doesn't mean the diagonal matrix D is invertible. Because, of course, diagonal matrix D will also have a 0 on its main diagonal, which means the determinant of D is equal to 0, hence non-invertible. Okay, so just be a little bit careful. That implication might seem true at first, but it is not from that example. Diagonalizable does not imply invertible. Okay, 5.6, easy money. 5.7, this is where the bulk of the criteria is going to be, and this is a big theorem in chapter 5. Here we go. Let A be an n by n matrix whose distinct eigenvalues are lambda 1, lambda 2, all the way up to lambda p. So this time we don't have n distinct eigenvalues. We have some eigenvalues with some non-trivial, non-1 multiplicity. So some repeats. For 1 less than k less than p, in other words, for some k less than p, okay, so one of these eigenvalues, the dimensions of this eigenspace is at most equal to the multiplicity of the corresponding eigenvalue. We can kind of see that in the previous example as well. In fact, we even hinted at this from before. Lambda 1 equals to 4 has multiplicity 1. So the eigenspace is dimension 1, right? 1 vector in the basis. Lambda 2 equals to 5 has multiplicity 2. So the eigenvector, eigenspace corresponding to lambda 2 equals to 5 is 2-dimensional. There's no way to have more dimensions than the multiplicity of the eigenvalues. There could be less so. That's when we run into problems. The matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspaces equal to n. This is our condition about having enough eigenvectors, right? Enough linearly independent eigenvectors. Because I have to be able to take enough linearly independent eigenvectors corresponding to the multiplicity of each eigenvalues. Again, here, let's roll back here. It means I have to be able to take out 2 linearly independent eigenvectors because the multiplicity corresponding to lambda 2 equals to 5 is 2. As you can see, because I needed to put that into my diagonal matrix twice, so I need 2 linearly independent eigenvectors. So this only happens in 2 conditions. 1, the characteristic polynomial can be factored completely into real linear factors. So we know that characteristic polynomials can be factored into either linear factors or irreducible quadratics. That is by the fundamental theorem of algebra. But to be able to factor completely down to linear terms, that might not always happen. But the time it happens, it means I have enough eigenvalues with enough multiplicity to add up to the number of the columns of A. Second condition here is that the dimensions of the eigenspace corresponding to each one of the eigenvalues is equal to the multiplicity of that eigenvalue. Again, kind of like that example before, the dimensions of the eigenspace corresponding to lambda 2 equals to 5 is 2, corresponding to the multiplicity of lambda 2 equals to 5. Okay. Lastly, if A is diagonalizable and beta k is a basis of the eigenspace for each k, so maybe this is kind of the important part of it. Okay, so for each eigenspace, we can find its basis. Then if we add up all of these vectors in all of the bases, that forms a eigenvector basis of Rn. So again, going back to the previous example, we can take this vector as a basis for the eigenspace corresponding to lambda 1 equals to 4. And we can take these two as a basis corresponding to the basis for the eigenspace corresponding to lambda 2 equals to 5. So if we collect all 3 of these bases, we found a eigenvector basis of R3. So the example we did here, we have on the screen right now, is that this and that is our choice of basis for the eigenspace corresponding to lambda 2 equals to 5, and this is our choice of the basis corresponding to lambda 1 equals to 4. Okay? That's really all there is to it. But this whole thing is built on the condition that if A is diagonalizable. Okay? So theorem 5.7 really characterizes everything we need to know about this terminology of quote-unquote enough eigenvectors, right? Enough linearly independent eigenvectors. So this gives us all of the conditions, and on top of that, it tells us if you collect all of the bases for the eigenvectors, eigenspaces, then you have a eigenvector basis of Rn. Okay, so let's check it out. Here's an example. This example is a very similar example to before, but it is a little bit different. Okay, so the number here is 4, 0, negative 2, 7, 5, 4, 0, 0, 5. When if you want to compare that to the original matrix, something is a little bit different, right? And it's actually only one number different. So instead of a, here, I'll point that out. Instead of a 7 here, oops, 7, 5, 4. Yeah, instead of a 7 here, we have a 2 in the previous example. One number different, but let's see how it plays out. We already seen how we found the eigenvalues, but just for the sake of example, let's go ahead and write this one out. So here, the characteristic polynomial, the determinant of a minus lambda I, this is equal to the determinant of 4 minus lambda, 0, negative 2, 7, 5 minus lambda, 4, 0, 0, 5 minus lambda. And we can see that we're using cofactor expansion on the third row, third column entry, so the 5 minus lambda. Okay. And of course, our cofactor calculation, so negative 1 to the, I guess, the 3 plus 3 times the determinant 4 minus lambda, 0, 7, 5 minus lambda. So very similar calculation to the one we did in section 5.4. So of course, the determinant here is just going to be 5 minus lambda times 4 minus lambda times 5 minus lambda. Okay. The point here is exactly that we have the same exact characteristic polynomial, and if we want to set this characteristic polynomial equal to 0, we can get that lambda equals to 5, 5, 4, again, up to multiplicity. So it's actually the same set of eigenvalues, the same set as eigenvalues. Okay? But just because it has the same size of eigenvalues does not mean automatically we have diagonalization. So we want to double check that. Okay, and we see that already a eigenvalue with multiplicity 1 is going to guarantee a eigenspace of multiplicity 1. There's just no way around it. So the only thing that potentially will not give you enough dimensions is this eigenvalue 5. Because I need this corresponding eigenspace to have dimension 2. Let's double check that. So for lambda, we don't need to give it a name anymore. Let's just go ahead and call it lambda equal to 5. The augmented matrix, 4 minus 5, 0, negative 2, 7 minus 7, and then 5 minus 5, 4, and then the 0, 0, 5 minus 5, augment it with 0, 0, 0. Well, this is going to give me -1, 0, -2, 7, 0, 4, 0, 0, 0. And of course, my answer column here. We can see that the first row and the second row are no longer scalar multiple of each other compared to the previous example. So if I want to do some EROs and maybe I'll write it down this way here. Again, normally I probably do these one at a time, but for the sake of spacing, I'll just go ahead and do them together. So we want to add row 1 to row 2 with a multiple of 7. That way I can get rid of the 7. And then, actually, I don't need to do both of these. Just one of these EROs is sufficient because this is going to give me -1, 0, -2. And then 0, 0, -2 times 7 is -14, plus 4 is -10, 0, 0, 0, augmented with the answer column zeros. Okay, so it's a minor change compared to the previous example in terms of how the eigenvector, the eigenspace calculation went for lambda equal to 5. But you can see the problem here because I have 2 pivot columns now instead of the 1 just like before. And because of that, I only have 1 free variable. I don't even have to calculate this any further because 1 free variable means I only have 1 vector in the parametric vector form. Therefore, the dimension of, I'll write this part down. So the dimension of the eigenspace corresponding to lambda equals to 5 just have to equal to 1, which is not enough. Because we need the dimensions of this eigenspace to equal to the multiplicity of the eigenvalue. That's it. Therefore, A is not diagonalizable by theorem 5.7. Okay, essentially, this condition is not met. Okay, so that's really all you need to do to check when something is diagonalizable. Now, obviously, if the matrix is much bigger, then there are more work to be done by the form of ERO, maybe in terms of calculating the eigenspace until you actually found the exact eigenspace here. But if it's not diagonalizable, a lot of times if you found the one eigenvalues and the corresponding eigenspace that does not have enough dimensions, then it's a easier task. Okay, but if you got multiple eigenvalues with various multiplicities, then you might have to do a little bit more work. That is at least how these problems are done in general. For the purpose of this class, for the purpose of practice, we're not going to go into a matrix that have 5 or even more eigenvalues, but in reality, you can be dealing with much more eigenvalues. Okay. Moving on, let's kind of see another example. Let's kind of tie in all of these things together. Here's a matrix B 11, negative 20, 6, negative 11. And our goal here is to find the B to the 2025. So we first need to find the diagonalization of B, because I certainly do not want to sit here and multiply this out 2025 times. If you want to do that, feel free to do that, but that will be the entirety of your semester gone. So the way we want to tackle this is, I didn't want to, okay, I did put 2025, perfect. Okay, we need to find the diagonalization of B, because if I can relate B to a diagonal matrix, then the exponent is more or less trivial. So I'm hoping for B to be diagonalizable. So when you want to find the diagonalization of B, here we actually want to be a little bit careful, as much as we know that 2 by 2 matrix are simple to calculate. We want to be careful of some boring algebra mistakes. Okay, we do not want to make too much algebra mistakes here. Here we go. The characteristic polynomial is the determinant of 11 minus lambda minus 20, 6, 11, negative 11 minus lambda. This is going to give us 11 minus lambda times negative 11 minus lambda. Don't forget the minus. Negative 20 times 6 is negative 120. Okay, unfortunately, we can't just set it equal to 0 and solve for it right away. Please don't make that mistake. A very common mistake is people setting it to 0 and then subtract 120 on both sides, right? And then, set both of these terms into 120. You cannot afford to make that kind of algebra silly mistakes at this stage of the game. What you have to do, of course, is FOIL things out, we're at the 120, and then set it equal to 0. So here we can FOIL this, and then I'll leave that to you here. But it's going to be negative 121 plus lambda squared plus 120. And this is going to equal to lambda squared minus 1. And now if you go ahead and set that equal to 0, you can just add 1 to both sides, take the square root. But it's going to give me lambda. Let's go with lambda 1 equals to 1 and lambda 2 equals to negative 1. Okay, the calculation here is not too bad to calculate, right? It's just a little FOIL. 11 times negative 11, right? 11 times negative lambda, negative lambda times negative 11, which is positive 11 lambda, and then negative lambda times negative lambda. So a little bit of algebra, but overall it's not too bad. Just make sure you do not forget to do this. Okay, it's a surprisingly common mistake. Anyways, we found our lambda eigenvalues, lambda 1, lambda 2. Let's just go ahead and find their corresponding eigenspace. By the way, at this stage, I don't need to go any further. I already know that this is diagonalizable just because I have a 2 by 2 matrix with 2 distinct eigenvalues. Okay, but my goal is to diagonalize my matrix B. So let's just go ahead and find the corresponding eigenspaces. So for lambda 1 equals to 1, it's going to be 11 minus 1, negative 20, 6, negative 11 minus 1. And this is going to give us 10, negative 20, 6, negative 12, augmented with 0, 0. Okay. And here's kind of a nice little trick if you want to leverage it sometimes. For a 2 by 2 matrix, or in this case, 2 by 2 matrix augmented with 0, 0, and we already know that I'm dealing with an eigenvalue. So I already know that these two, I have to be able to cancel one of the rows out. In other words, both of these rows are multiple of each other. So I can write out the exact ERO. Okay, and of course the ERO is just going to be add row 1 to row 2 with a multiple of say negative 6/10. Okay, some fraction, you can easily cancel one row with the other. You can even multiple, you can add, whatever is not the hardest thing to do here. But because our theory guarantees we can remove the second row, we can essentially do some ERO to get rid of the second row. Some presentation of this material just allows you to say, hey, I can just go ahead and cross off the second row because I know after a ERO, I'm going to get rid of that second row. And so the result is something that looks like this. Just a little bit smaller here. Okay. The point I'm trying to make here is that the benefit of having only two rows is that to get an eigenvalue, you need to be able to get rid of one of the rows because you cannot have a pivot in both rows. So that being said, you can erase any row that you like. This turns out to be the key in doing complex eigenvalues because complex operations are much more challenging to visualize right away. So if you're interested in that, take a look at section 5.5. Now, anyways, let's continue with our example here. After getting rid of this by some ERO, you can go ahead and just label EROs. We can see that 10 is going to be a pivot, therefore x2 is going to be free. I'll just write free here. From there, we can see that x2 is free, right? And x1 is, I guess, add 20 over, divided by 10, so 2x2. So therefore, v1, this is equal to x2 times the vector, looks like what, 2, 1, for all x2 in R. And we're done. So this one is pretty simple. The other one is pretty much the same way, especially if you go ahead and leverage this. So let's go ahead and write that down. Lambda 2 equals to -1. Let me change the color here. Lambda 2 equals to -1. And then I have 11 minus -1, -12, 6, 11, -11 minus -1. And this is going to be 12 minus 20, 6, -10, augmented with 0, 0. Okay, same logic. I can just go ahead and erase the second one. Okay, or if you want to go ahead and write that down, you can. It's gonna become some EROs. Oops. And then you get 12, -20, 0, 0, augmented with 0, 0. Okay. Before we go any further, I do want to reiterate, you can only kind of do this stuff in a 2x2 matrix. In a 3x3 matrix or higher, unfortunately, it doesn't work that well, okay? So be very careful on your EROs in any matrices bigger than 2x2. Okay, so 3x3 or higher, you cannot use this trick. I just want to say this one more time because I know people are going to try to do that on inappropriate matrices. Just be careful. Just don't let that be you, as I always say. Anyways, so here we have one pivot. We have one pivot, and still it means x2 is free. That means x1 is equal to, again, add the 20 over, divide by 12. Let's put 20 over 12. x2 And if you simplify that fraction, divide top and bottom by 4, 5 over 3, x2, and then x2 is 3. Okay, so therefore the v2, the eigenspace corresponding to lambda 2 equals to -1, that is equal to, actually, why don't I just put -1 here, just so I don't, yeah, v -1 here. This is equal to x2, and then the vector is 5 over 3 times 5 over 3, 1. And this is for all x2 in R. Okay, so I found my two eigenspaces corresponding to lambda 1 equals to 1 and lambda 2 equals to -1. The purpose of this is for me to be able to choose a correct value for P, a correct matrix really for P, the invertible matrix. So from here we can pick a diagonalization for B. So lambda 1 I choose to be 1, lambda 2 I choose to be -1. We can go ahead and write that one down. And then because what I want to do next, I need to find P and P inverse. So I want to pick integer value P. So for V1, it's not too bad. I can just pick 2, 1. For V2, I want to be a little bit careful. Instead of picking 5/3, 1, I'm just going to choose x2 equals to 3 here, and then choose the vector 5, 3. Okay, 5, 3. Pick x2 equals to 3. Okay, and from here, I can then easily calculate P inverse because the determinant of P is just going to be, I'm just going to go ahead and write this down. Just going to be 2 times 3 minus 1 times 5. And then the alteration to P itself is going to be 3, 2, -1, -5. Okay. 2 times 3 minus 1 times 5 is just 1, so nothing happens there. So the matrix is P inverse is just going to be 3, -5, -1, and 2. Okay, and finally, we're ready to make our calculation. Let's just go ahead and write this down. B 2025, this is equal to PD 2025 P inverse. And that is just going to equal to the P matrix, which is 2, 1, 5, 3, times the diagonal matrix to the 2025 power. But again, that's the beauty of the diagonal matrix. It's just 1 raised to the 2025 power, 0, 0, -1 raised to the 2025 power, times P inverse. So I guess that's 3, -1, -5, and 2. And from here, this is really just going to be 2, 5, 1, 3 times the matrix 1, 0, 0, -1 times the matrix P inverse, which is 3, -5, -1, and 2. And you can just go ahead and multiply these in order. So multiply that together, and whatever you get, you multiply by this. But we actually don't need to. This is kind of a funny little problem, because this here, after raising D to 2025 power, actually just get D back. And this is P, and this is P inverse. So I really just have P inverse dp, oops, sorry, got that flipped, huh? P dp inverse, and we know this is actually just gonna be B. So the result is just gonna be the original B matrix, which is 11, negative 20, 6, negative 11. And we're done here. All that feels kind of like, for a little drop of blood here, we, after 2025 power, we get back to the same matrix B. But in the term of example, this is really how we can tackle this kind of problem. Just kind of the result is more or less for the laws in some sense. Okay, and you can double check this too, simply by taking B to the second power, that you can crunch out by hand, and then taking B back to the third power, again multiply that by hand, just like how we started the section, and you realize B to the third power is B itself. Kind of interesting, but that's one way to do it, and you certainly can do that with third power, but not with 2025 power. So still, this technique is kind of fun and is useful. Okay, even though this question in particular is kind of for the laws. All right, hopefully this one ties in everything together, and hopefully you can see all of the steps, all of the procedure in calculating eigenspaces, and of course diagonalizing a matrix. Okay, so this is the material that you are responsible for. You need to, get all these things together and practice this task. It's really not a hard conceptual problem. You just need to, go ahead and practice exactly what to do in each one of these steps. As you can see, most of these are built up from, very old material, as we did in earlier part of the semester. So please practice this. Okay. Now, this is basically it for the section, and for us is basically it for the for our class relating to diagonalization, relating to eigenvalue, eigenspace, eigenvectors, all the eigen stuff. Okay, but for the sake of introduction, I'm going to go ahead and tell you a little bit more about what else we can do with this topic, or similar topics. Okay, what does this actually benefit us in the long run, in the grand scheme of things? Why do we bother talking about linear algebra in terms of eigen stuff? There are some interesting application in terms of optimization as well, but I'll leave that for your own discovery for another day. But here, one of the more interesting things that our book doesn't quite go into detail about is the Cayley-Hamilton theorem. Cayley-Hamilton theorem says every n by n matrix A satisfies its own characteristic equation. So again, our characteristic equation, A minus lambda I equals determinant of A minus lambda I, that's a polynomial, right, setting equal to 0. In other words, we're looking at the zeros of this polynomial. So for example, in the previous, I think example 3, when we have matrix A equal to this particular example, actually this is like the very, a much older example, not example 3, right? Example, not this one, but example 1, I guess, which really is an example in section 5.2. Either way, here's a example. Matrix A, and we calculate the determinant of A minus lambda equals to 5 minus lambda squared 4 minus lambda. And if you go ahead and expand the multiplication out, right, FOIL everything out. Oh, just realized I did have a little typo here. These are still lambdas, right? Force of habit, I suppose. Okay, if you go ahead and expand that out, you do have a polynomial in terms of lambda. This is why determinant of A minus lambda is called the characteristic polynomial. But then, if you go ahead and set that equal to 0, you have the characteristic equation. What we're saying about Cayley-Hamilton theorem is that the matrix A satisfies this equation. So if I plug in A into where lambda is, I'm also going to get 0. And of course, this 100 need to be written as 100i, right? Same way we treat constants with, involving in matrix addition and subtraction. So as you can see, we have negative a cubed plus 14a squared minus 65a plus 100i equals to 0, which is essentially the characteristic equation of A. So Cayley-Hamilton just says, hey, your matrix A has to satisfy its own characteristic equation. There's some interesting application to this. I'll leave you, again, for your own discovery later on. In a class like, say, 347. So stay tuned for that. The next thing here is we can then talk about, we discussed this already, but because now we can talk about powers in a relatively easy way with diagonalization, we can then refer back to, again, e to the power of a, right? To talk about that, we need to leverage the Taylor series from Calc 2, which I'm sure we're all familiar with, and this is all, everybody's crowd favorites, right? So if you have the Taylor series representation of E, we know this converges everywhere, but of course here we're talking about matrices, so there's still a bit more mathematical theory we need to kind of sweep under the rug. But for now, if we kind of work with this formula, we can then raise E to a matrix power, and that's just replacing the x with A. So then by Taylor series, it's just gonna look like this when we expand this out. And the beauty of this is that if A is diagonalizable, then we can do a very similar calculation to calculate each power of A. Right, again, the idea here is that if A equals to P d P inverse, then we can say that, for example, A to the, all right, we can do this in general actually, A to the nth power is equal to P d to the nth power P inverse. And you can actually do a little bit more simplifications to eventually come out to your whole summation on the inside of your determinant to the power of n. Not determinant, sorry, matrix D to the power of n. Okay, so more maneuvers you can do, but the whole point I'm trying to make here is that now that you have a way to efficiently calculate powers of a matrix A, infinite powers of a matrix A, you can actually define the expression, exponential expression, e to the power of a matrix. And this, of course, you will use in much higher level analysis when you're talking about, limits, derivative, integrals, right? All that good stuff. Laplace transform even in a class like differential equation. Okay, so very, very interesting stuff later on in class, like say 364A. Sometimes I don't believe you would touch on this topic, but sometimes Math 370A. The last thing I want to mention is a slightly bit more advanced of this idea of diagonalization. We want this concept, but as you can see, sometimes the condition is rather challenging, right? Even if you change one number from a 2 to a 7, for example, you lose diagonalization. You lose diagonalizable. So what happens if a matrix is not diagonalizable? Well, we want to leverage that, leverage the concept of diagonalization, but a generalized form, which is called Jordan canonical form. A Jordan canonical form. And the way this works is that instead of having each eigenvalues on the main diagonal entry, we're going to treat them as each of these eigenvalues, we're going to write them into what we call Jordan blocks. So they still feel like a diagonal entry, but then your matrix is much bigger, as you can see on the example on the right. But each one of these blocks are n by n blocks that have the eigenvalues on the main diagonal, but a 1 right above each entry is on the main diagonal. Why this is not stamped correctly? Here we go. Okay, a 1 on top of the main entry on the main diagonal. So here, this is another Jordan block. Okay, one last one here. So all these are Jordan blocks, and if you look at the block as a whole, these still rest on the main diagonal of this enormous matrix that we're looking at here. So this kind of follows the idea of the diagonal matrix, except for here we have to kind of look at this matrix as a big matrix broken down into smaller blocks. Okay, so more tedious, more work, but it's more general, it's more powerful. So again, I'll let you explore that in future math classes. So there's a lot of things happening in the same set of series. We can extend this, we can do more calculations, we can come up with more intense stuff. But this is why we learn linear algebra. So it set us up for something more interesting, more useful, more applicational in the future. Okay? Anyways, this is it for me for today. I will see you guys later.